Okay, so just a very short video to just go through the topics I had mentioned in my email 3 days ago on what to revise from POSA. Of course, it goes without saying, and I hope you all have been spending some time on the microwave office software to be familiar with it so that it doesn't take too much time for you during the exam. So please do spend some time if you have not done enough of it before the exam at 3 p.m. tomorrow. So I just want to just quickly flash through these sections, not actually go through or discuss anything, just to remind you of what are the things we are looking to revise. The first set of sections on chapter 2, of course, obvious. I mean, this is just the basics of the transmission line, the transmission line model, what it consists of, how you get a wave equation, these kind of things. There was a question in the last exam on this discussion of this transmission line. Of course, it was an open-ended question, but most of you didn't even try it. So anyway, this is really just for revision in general to familiarize yourself with the idea of transmission lines. And then once you go to the simple picture of the lossless transmission line, which is the case where this R and G are 0, that is the resistance per unit length and conductance per unit length is 0. You get a simpler form, but the wave equations, do exist in the general case as well, as shown here in equation 2.8 for the voltage and current, and the ratio of voltages and current waves traveling at any point is equal to the characteristic impedance. So this is a section of the lossless line. This is the one which we mostly deal with, where we assume the losses are either 0 or very, very small, that we can ignore them. And then in that case, you have this characteristic impedance of the line only depending on the ratio of inductance per unit length and capacitance per unit length. And this is what the main wave equations you need to be sort of familiar with in general, how waves propagate. Okay. Then we move on to section 2.3, which is about the terminated lossless line. So this is now introducing a boundary condition which allows to have a reflection, so that when you have a section of transmission line terminated by a load impedance ZL here, then what does this section of transmission line do to that impedance if one is viewing from the other end? So how a section of transmission line changes or transforms the impedance of a load on one end to the other end, and how it depends on the length. So that is discussed here essentially by looking at what happens at the boundary condition, that the voltage ratio of voltage and current should be equal to the impedance which is set there, and from that you get the expressions for what the impedance is, which is over here, the Z in, ultimately giving you this equation 2.44. And if these are of a particular length, then you get some special case results, quarter wave and half wave. So those things we have seen, which is then followed up by section 2.5 on the quarter wave transformer itself. And I think we have gone through the quarter wave transformer enough number of times, but it's good to go through it again. It's a very useful and general circuit, and there is a later section on quarter wave transformers talking about impedance matching in section 5.4 as well. So go through this as well. The section 2.6 is the case where you have both a load and a source, and what if both are mismatched, right? So this case here, both the source resistance, which we typically assume to be Z0 in the conventional case where the transmission line is Z0, it's 50 ohms, source impedance is also 50 ohms. Here, this is the most general case where the characteristic impedance of the transmission line is different than the impedance of the load, at one end, and it's also different than the impedance of the source as well, the most general case. So then you can have reflections in multiple places. This is, of course, in some sense, the most general case, because you'll always never have perfect matching anywhere. But it also, in some sense, a more artificial case, because you don't really want to be in a situation where everything is mismatched. But it's sort of useful to see what happens here in this case as well. Okay, so then that's about chapter 2. Then one moves on to chapter 4, which is section 4.3, the scattering matrix. And again, it's a very straightforward concept, but a very useful thing, and the most natural language in which we describe how a particular microwave network behaves. And this comes from the idea that it's difficult to measure voltages and currents inside particular circuits and to define impedances and things like that. So the most natural quantity one measures are incoming and outgoing waves at the boundaries. So a scattering matrix basically relates all the outgoing waves, which we call as this V index n minus, and how it is relating to all the waves which are coming into the network. It is completely equivalent to other matrices like the impedance matrix and admittance matrix as well, and one can transform from one to the other. But this is the most common one. This is what we measure using a vector network analyzer. You've seen this in class. This is the picture here again. And that is the quantity it usually gives you. And of course, we can interconvert these things. So just the general idea of scattering matrix is good to revise through. In terms of all the properties, the mathematical derivation, you don't have to worry about it at this stage, just to know that what happens when you have a lossless system, what kind of matrix you get, and what when you have a reciprocal system, which is typically the case for most passive networks. So those kind of things is useful to revise and remember. Then we move on to section 5.4, which is the section on impedance matching using quarter wave transformers. So right here. So this is again an extension of the previous discussion on quarter wave transformers. So you can just look at that. Talks about the bandwidth. There was a question in the last exam about multi-section impedance transformers using several quarter wave sections. So again, useful thing to revise. Then we move on to chapter 6, which is section 6.1 and 6.2 on resonant circuits. Again, we have gone through this many times, and I hope these concepts are very clear about the series circuit and the parallel circuit. What is the definition of the Q factor, and what is the definition of bandwidth? So, and the expressions for these things. It's useful to revise these things, and what actually happens to the impedance on resonance and when it's a series resonator versus a parallel resonator. Those kind of things it's useful to revise again. And all of this, you should keep it in the context of how you can measure these quantities in microwave office software, or also know in general how to define, say, the reflection coefficient for that particular case. This goes on to the next section of making such resonances using sections of transmission line. So this is basically when you create a boundary condition on one end and then look at how the impedance varies, it shows the same kind of variation as that of a series LC circuit or a parallel LC circuit. So that is the equivalence you get. So you can use these also as resonators. They also show the same properties, but of course, not over the entire frequency range. The LC resonator has only one resonance, but a section of transmission like you can have several resonances based on how many wavelengths you are fitting into the thing. So the equivalence of a transmission line resonator to a series or a parallel LC resonator is only local in frequency. But again, as we were discussing, normally we are talking about resonances which are sharp. So all the action is confined to a very small range of frequencies. So it's a perfect to make that model. And this section sort of discusses that and how you compute the equivalent inductance and capacitance for an equivalent circuit to construct an LC for a transmission line resonator. So clearly it depends on the characteristic impedance and the frequency and things like that. Okay. So that's chapter 6. And then finally, chapter 7, which is as these power dividers and directional coupler. So there I had asked you to just look at section 7.2 and sorry. Yeah. The T-junction, I mean, maybe, section 7.1 also just go through because it kind of gives the general scattering matrix of these 4-port systems and how under different conditions you get different kinds of devices like 180-degree hybrids and 90-degree hybrids and power dividers and Wilkinson power dividers. So this again, we discussed extensively earlier. Just good to revise the basic ideas behind it. I would even recommend that you draw some of these circuits in Microwave Office and see that they behave as described in this section. Okay. So yeah, so I just wanted to just say a few things. I mean, I sent you this list already. As I mentioned in my last email sent earlier today, that the exam is going to be open book. So the idea really is not to see if you have, remembered stuff, but more if you have understood the things. So the questions will also be of that nature. You're free to consult any book. I would recommend you have a copy of POSAR. It's good enough, but I mean, I will repeat this, of course, at the time of the exam, but I don't expect you to try and Google the problem on internet and try to find a solution. So please don't do that. Please do check all your access to the Microwave Office software tomorrow, maybe a little before the exam. I'm trying to get the room AG69. I think that would be a convenient place to do this, but I will confirm this tomorrow by lunch after talking to the security staff. Yeah, I mean, you are also free to keep your notes as well. And if you have any technical difficulties with accessing the Microwave Office software, please email me. And I guess for some of you, we have to make arrangements to access it on a different machine because you don't have Windows laptops. So we'll take care of that. Okay, I have not gotten any email from any of you about choosing the Monday slot. So I'll wait till 10 p.m. Tonight, and then if nobody's response, then we'll just do, anyway, we'll do it on tomorrow at 3 p.m. And I'll give that one person a separate exam on Monday. Okay, so that's it. So good luck with the preparation, and see you all tomorrow.